Welcome to Session 11, Inequalities and Absolute Value Constraints. This lesson develops mathematical reasoning that stays reliable when a problem looks unfamiliar. You will learn to reverse inequality signs when required, to translate absolute value as distance, and to report interval solutions. These are connected habits, not isolated tricks. Keep a pencil ready. We will build a mental model, use a repeatable method, solve a demanding example, diagnose an error, and finish with an independent checkpoint. Start with this principle. An inequality describes a region, not just boundary points. Use this visual structure. Boundaries is greater than intervals, is greater than test points, is greater than endpoint rules. Read every symbol and label before calculating. The first goal is to reverse inequality signs when required. Connected to the second goal, translate absolute value as distance. Correct calculation begins with correct interpretation. When the surface details change, search for the same relationship underneath. Transfer means choosing the structure from evidence rather than waiting for a familiar-looking example. Step 1. Find boundary values. State the target and preserve its units or conditions. Step 2. Mark undefined points. Use a separate line so signs, factors, and labels remain visible. Step 3. Test one point in each interval. Keep the reasoning efficient, but never skip an operation that could hide an error. Step 4. Include boundaries only when allowed. Verification is part of the solution because it tests the answer from another direction. Signal 1 is divide by a negative. Respond by remembering. Reverse the inequality. Name the response before calculating. Signal 2 is absolute value is at most C. In that case, use the inside interval. The form tells you which tool fits. Signal 3 is absolute value exceeds C. Remember, use the outside raise. This separates plausible work from valid reasoning. If you cannot name the signal, pause and classify. A deliberate choice of method is usually faster than repairing a rushed setup. Here is the challenge. Solve x plus 1 over x minus 2 is greater than 0. Restate what is requested before touching the choices. The first move is find boundary values. Apply it directly to the quantities and conditions in this problem. Now use the core reasoning. Critical points are -1 and 2. The quotient is positive on the outer intervals, excluding 2. Keep each equality, comparison, or unit conversion visible. Pause for a midpoint audit. Check copied values, signs, units, restrictions, and whether the current result is the requested quantity or only an intermediate value. Continue by applying this control. Test one point in each interval. The explanation supports one option without relying on its position. The mathematical conclusion is x is less than -1 or x is greater than 2. State it with any required units, interval notation, or restrictions. The final answer is x is less than -1 or x is greater than 2. Compare it with the exact target and reject any choice that represents a common intermediate step. Verify from another direction. Test one value inside and one value outside the reported set. The check should use evidence independent of the original calculation whenever possible. Try this checkpoint without copying the example. An upward minus opening quadratic is positive at a point between two real roots. What does this indicate? Decide which mathematical fact controls the answer. Pause and write one line of reasoning before committing. A visible decision is easier to inspect, explain, and correct than an unsupported guess. F-focused hint. With two simple real roots, an upward quadratic is negative between them. Use the hint to repair the setup, then finish the reasoning yourself. The accepted answer is A sign minus analysis or root calculation error. Explain why it works, and name the earliest line that would reveal a likely error. The central message is to reverse inequality signs when required. Combine that with the discipline to translate absolute value as distance. Finish by remembering to report interval solutions. A result becomes dependable only when the method and verification are both clear. Reflection. Which endpoint is included, excluded, or undefined? Name the exact point where an incorrect path would first become visible. Practice one fresh problem for 8 to 12 focused minutes. Keep the work readable, verify independently, and carry the routine into the next session. Before moving on, close the notes and explain the method aloud from memory. Then invent one small variation, predict how the answer should change, and verify that prediction with a complete calculation.